Good morning, everyone. Today we're going to finish off indefinite integrals, and I want to do some practice at some other situations. We're also going to do an example of an indefinite integral being used in a practical context. Basically, it's an acceleration velocity question. Next, after that, then we'll do some applications that are not velocity related. So that's kind of the goal. So let's get right into it. Let's do a trig one. Right, we know that from previous questions like this, we've known that when you have something like this, that what you have to do is you have to kind of fix it so that you can use a standard integral. And right now this says secant of a secant take away 2 tan. First thing I would do is distribute. So it's now secant squared x take away 2 secant x tan x. And actually, that's all I need to do. I do not need to go hunting for trig identities and to turn any of these things into anything else. I do not need to do that because each of these is over here. For instance, isn't to the antiderivative of secant squared tan x. What is the antiderivative of secant tan? My hand is hiding it, so you're going to have to do it without saying it. But it is in our table. Secant. Say that again.
Secant?
Yeah. So negative 2 secant tans is negative 2 secant. And then you just tag on a plus c and you call it good. Pretty straightforward. Sometimes you have to know when not to do something, because there is a temptation when you see this to say, oh, I'm going to look at that big list of identities and find that I can call secant squared 1 minus tan squared, and I can call this thing here something else. And all you'll do if you did that was change it into other things. And those other things that they change into, you don't know what the antiderivatives are. So you've actually went down a rabbit hole, right? You've went down a place that never takes you anywhere. So you need to, whenever you do something, just hold on a minute and say, wait a minute, I'm done. I can get these. You know, don't make my life harder if it's not necessary. Right, let's move away from trig. Okay, what do you think might be a good idea in this particular question?
Split the fraction.
Oh, that's an interesting strategy. And I'm assuming that you were thinking that, agreed? Okay. Won't t cubed on the top divided by t squared on the bottom simplify down to just being t? And won't t on the top and t squared on the bottom, don't they cancel down a little bit and you get 1 over t? Now at this point here, shouldn't you be saying, woohoo, aren't these guys doable? Power roll for the first one, add 1 to the power and divide by the new power. But what would 1 over t get you? Oops, hide it. What would 1 over t get you?
Natural log of t.
And then just stick in a plus sign, call it good. And that is a perfectly valid, and actually I kind of like that way of doing it. But not all of you might have seen that way. So let's look at a different pathway. Right? So we won't do it this way. We'll see if there's another algebraic way of eventually solving this. What other method could I use for this question?
You could turn it to 2 to the power of -2.
Okay. And distribute it through. Let's see what you get. T cubed times t to -2 gets you t. T, which is really to the 1 power, times this, gets you a really ugly looking -1. And what you have to realize that that guy is better written as that guy. And then you end up with the same answer. Do you see that's just 2 different routes to the same destination? But algebraically, they're a little bit different. This, it needed an extra step. I had to realize that this guy has to be written like this guy so that I can find this antiderivative. Well, you might say, well, what's wrong with t to the -1? Why can't I just try and find the antiderivative of t to the -1 on its own? Well, let's try it. Let's do the power rule on it, right? According to the power rule, you add 1 to the power. So that power now becomes t to the 0. You then divide by the new power. Can you see that that's not going to end well? This is the only form of a power of t where the power rule does not work, right? T to the -2 works, t squared works. T on its own works, but t to the -1 doesn't work. And so that's why this had to be changed. Are we good? Any questions so far? Okay, let's this is a question similar to question 5 in the homework. It's not quite the question, but it's very similar to it. And it's not your typical question. In this question, you're told that the integral of cos squared dx is 1/2 x plus 1/4 the sine of 2x plus c. And you're being asked to make one of 2 choices. What this says is true, or what this says is false. And you're being asked to check whether it's true or false by differentiation. So this, in a way, kind of shows you the connection between differentiation and finding antiderivatives. Going this direction, from cos squared, the integral of cos squared to this, that's basically finding an antiderivative. But if I start with this and I differentiate it, shouldn't I get that? Does that make sense? If you start with something and you integrate it, if you differentiate the integral, shouldn't you get back to the guy you started with, right? It's like a little circle of life thing, right? Both directions work. So to solve this problem, is it true or is it false? I am going to take the 1/2 x plus 1/4 the sine of 2x plus c. I'm going to take that guy and I'm going to find his derivative. Now, if his derivative ends up being cos squared, I'm going to choose the true box. If the derivative of this function ends up not being equal to that, then I'm going to hit the false. So here it goes. If you differentiate a 1/2 x, you get a 1/2. If you differentiate 1/4 the sine of 2x, it's a chain rule. You get 1/4 the cosine of 2x times something else, don't you? Times another what? What's missing?
You have to use the chain rule.
Correct. And what is the derivative of 2x? Because that's what the chain rule asks you to do.
2.
Right. And won't that quarter times 2 get you a half? What's the derivative of plus c?
Zero. Goes away.
Just goes away. Now, you're going to look at that and you're going to say to yourself, that does not look like cos squared x. And you will hit the false box, but you will be wrong. And let me try and show you why. If you pull out a common factor of a half, you get that guy. Does anybody recognize that that guy is one of the weird trig identities? One half, 1 plus the cosine of 2x is a trig identity. What's it equal to?
It's like cosecant. Something.
Cosine squared x. And just go looking for it and you'll find it is. So in my case, you would hit the true box. So you're going to do a question 5 in the homework that's going to look very like this. And you're going to take whatever they give you on the right hand side and you're going to differentiate it, and you're probably going to get some that looks not unlike that. But trust me, whatever that is, it does turn into something nicer, and that thing that it turns into may or may not be that guy, whoever it is. So a little bit cryptic, but that's as much help as I want to give right now on that question. Okay, here goes. There's really not too many things we haven't done. This one here. Although this is big, it's actually, for the most part, pretty easy to do, because I don't need to do any preamble. I don't need to fix it algebraically much. Almost all these pieces we are ready to do antiderivatives of. Okay, let's try each one. What about this guy? Well, isn't he just a bog standard power rule? Add 1 to the power, divide by new power. What about the plus 4? No biggie. Leave that guy for a minute. My friend e to the x. Okay, what about 8 over 1 plus x squared?
8 times inverse tangent.
I heard, yeah, is that what you were going to say as well? Emma, were you going to say that? Yeah. Isn't it nice when it's nothing really except, you know, it's in the table, right? Or a multiple of it at least, right? Now, the only guy that I've kind of put this funny little dot on is this guy here did need just a tiny little tweak, right? You had to do just a little bit so you could use this, right? In this case, I hope you all would realize that it needs to be turned into a negative power, agreed? And then it's a power rule. And the power rule is add 1 to the power and divide by that new power. Have you noticed that it now becomes, have you noticed that it now becomes positive? Because 2 negatives cancel out. Is that the best way to write this one term here? My style point rule? No. What should that be rewritten as, just so that it gels with the original question?
3 over
3
X.
over X.
Right. So are we all getting a little bit comfortable about what I call style points? And basically make the answer look like the original, right? So if the original's got square roots in it, don't leave things as 3 halves or x to the half, right? Turn them into square roots, right? If things are 4 over x cubed, make sure your answer's something as a fraction, right? That kind of thing. But not too many weird things going on there, right? Pretty straightforward. I think actually I've got about 2 more things I haven't done. No, 3 things I haven't done. Okay. So first one is a trick question. I am warning you, it's a trick question. Sorry, thinking caps on. Now, how are we going to tackle this question?
Could you split the fraction again?
Okay, so are you thinking about that?
Yep.
Good. And then you get that. Now, what could go wrong here? Because you didn't fall for the trick question. What could have gone wrong? And this is the correct answer, right? Happy face, correct answer. This, you could have done this. Oh yeah, 1 over x is a natural log of x. So 1 over 5x is just the natural log of 5x. Now, I hope nobody here thinks that's a good idea. But unfortunately, a lot of students do think that's a good idea. That is not correct. Do you see that you have to, and this is deliberate, do you see you have to think of that as this guy? And that makes sure that you break it the right way. And you might falsely think that this is the same thing as that, right? That algebraically 1/5 of this is that. That is not the case. Do you know these 2 things are totally different from each other? I mean, if I wanted to make this into something else, the only thing I can think of breaking it down into would be the log of 5 plus the log of x. And if I wanted to rewrite this in a different way, the only thing I can think of that you could use would be to call it that. Do you see that there's nothing even vaguely similar about what that means mathematically and what this thing means? Very good. Now, in that same vein then, here are some other versions of that same mistake. You do not do a power rule on 3x all squared. Don't you have to call it 9x squared? And then you can do the power rule on it. So that would be what? Eventually 3x squared plus c. So what I'm saying here is do not have you noticed that standard integrals have x's? They don't have 1 over 2x or 1 over 5x, right? It's 1 over x. And powers are x cubes and x squareds. They're not 2x cubes or 2x squareds. And so if it looks like that, you have to fix it before you try and use the antiderivative rules on it. So that was one of the things I wanted to do. Where are you? There's another one in here. Oh. There's a function called the hypersine function. It's sine with an h after it. It's called the hypersine function. The only reason I am telling you what its integral is so that you can do, where the heck is it? So you can do question 9. You've probably never seen the hypersine function. We don't do it in Calc 1. It's a very rare function. It doesn't get used very much, so it's just easier not to talk about it, and so we didn't. But just in case the odd thing comes out, it does have an antiderivative, and its antiderivative is the hyper cosine function. And there is a hyper cosine function, and it gives you its antiderivative is the hypersine function. And I think I'm going to put little brackets around that just so you can see that sine h is the whole name of the thing. It's not hx, it's sine h, hypersine function. There's something which is probably another reason why we don't do it. Do you notice in both cases the answer is positive? That's not a mistake, they are. Can you see how that might confuse you when you're trying to remember the antiderivative of sine and cosine? Because if you start entering another function, the hyperfunction, then that just muddies the water totally, right? So you only need to know this for question 9, and then you can put it in a little box and look it up and don't look inside it for a long time, right? Because it's a one-off deal, and it's just so that you know, we're covered for one of the questions. Are we okay with that? Hypersine, weird function, ain't going to look at it again for a long time. And here is another function. That guy. It's not that guy. If you want to do that guy, you just add 1 to the power and you divide by the new power and you're finished, right? That's this guy. It's 5 to the power of x. Can anybody remember, this is going sideways, how to differentiate 5 to the power of x? You did get 5 to the power of x, and what else did you get?
Wasn't it like something to do with logarithms?
It was. What was it?
It was
Hey,
like,
you're so close.
it was like, wasn't it like 1 over natural log, something like that?
Any? Oh, you did really good. Where
Take
you
the
got to
natural
is
log
good.
of both sides.
Say that again.
Take the natural log of both sides.
Okay, I'm just going to prove this one to you so that when I do the antiderivative, it makes sense. Otherwise, it's just magic, right? So here goes. And what you said is correct. We're going to show you how you would tackle this question. It's called logarithmic differentiation. So you take the natural log of both sides. According to the law of logs, can't the log of 5 to the power of x be written as x times the log of 5? Right, that's the third law of logs. You then take both sides, you take their derivative with respect to x. Well, the derivative of a log is 1 over y, and then you go to y by dx, and the derivative of this guy is log 5. You know, like 5x gives you 5. You then multiply both sides by y, and then you replace, oops, it's an x, and then you replace the y by 5 to the x. So the derivative of 5 to the x is this guy here. Right, so it's 5 to the power of x times log 5. The antiderivative of this guy has a 5 to the x in it, has a plus c, but it has one difference. Do you know that when you differentiate, you do one thing, but when you find the antiderivative, you do the opposite of that thing? When you differentiate, do you see how you multiply by log 5? So what do you think you should do when you find the antiderivative? Not multiply by log 5, but
Divide.
divide. So here you go. So I'll stick in my little list here what a to the power of x is, where a could be 5, for instance. The antiderivative is a to the x over the natural log of a. And so that's pretty much me covered all the loose ends. Right. So what's left? Well, we're going to do an application of antiderivatives and then some using velocity acceleration kind of thing, and then applications just using, oh, Nicholas, and then applications in other context. Okay. Suppose I tell you that you have a moving object and its acceleration at any given time is 6t plus 2e to the t. So can you imagine this object that as time goes by, its acceleration is continuously changing, right? So if you had an object that was being shot off, who knows, into space, it may well have a model that looks like this. It's not just a fixed, oh, its acceleration is 5, its acceleration keeps changing. Now this is what makes calculus different from some of the early physics that you got. When you do physics questions, wasn't the thing its velocity was 20 meters a second and its acceleration was 5 meters per second, and everything was just a fixed number that didn't change? That would be the typical kind of questions. Now we're making the world more realistic. We're making the acceleration change through time. And let's say that this moving object, that this formula works for the first 4 seconds. We are then going to be asked to find the velocity of the function at any given t, right? When you are told that the velocity at time 0 was 2. And then we're going to find the distance traveled in the first 4 seconds. That's our second question. All I really know is the acceleration of this object. That's pretty much all I know. And I know that its velocity at the start is 2, say 2 meters per second. Yet with that limited knowledge, I am about to show you how to find the velocity, right? What's the velocity of that object at any given time? And then I'm going to be able to tell you how far it travelled in that 4-second period, right? Now, before we show you the math of this, if you take velocity function, what was the derivative of the velocity function? This is Calc 1. If you're told the velocity function and you differentiate it, what do you end up finding?
The acceleration.
You find the acceleration. So if you take this guy, right, and you differentiate him, then you get this guy, right? What do you think you would get if you take the acceleration and you find its antiderivative? Then shouldn't you get the velocity? Do you see how it works in two directions? We're now working, if one of them's like working downhill, we're working uphill, right? So to get question A, to find the velocity function, we always integrate the acceleration function. In this case, we're going to integrate 6t plus 2e to the t dt. So far, so good. Now, I haven't made this, this one is very similar. I should give you a question number so you know. The guy I'm looking at here, darn it, he's around here somewhere. And this is very like question 4, right? Okay, so back to this question. Antiderivative of 6t, it should, I hope we're getting to the point where it gets really quick to do the obvious ones, right? That you're not add 1 to the power, divide by new power, and it's taking you 30 seconds to think it through. You should, a lot of these you say, yeah, done it, seen it, there's the answer, right? I can do it quickly in my head. There is a problem with the velocity function, because when you take antiderivatives, don't you make a plus c happen? You can't avoid it. But I don't want a plus c here. I want a number. Now, it might be plus 1, it might be plus 0, it might be minus 20, but I need a number. Well, that's why you're told this fella. If I tell you that the velocity at 0 is 2, shouldn't I be able to plug it in here and then figure out what number c is? So let's figure out what that is. The velocity at time 0 is 3 lots of 0 squared plus 2 lots of e to the 0 plus c, and we're being told that it equals 2. Well, that's nothing. Isn't that 2 times 1, so that's 2. So that makes that relationship. You agree that nothing plus 2 plus c equals the answer 2? And solving for c, we get a rather boring value. In this one particular situation, c is 0. Can you imagine if I made this number 20 or 10, c would turn into some totally different number each time. So the 0 is not significant, it's just that's this one particular answer. So I now know the correct, complete answer to what the velocity is. It's 3t squared plus 2e to the t. Technically plus 0, but nobody writes plus 0. So although I only know the acceleration at the start and I know one particular velocity, what I really know now is quite important. Don't I now know how fast the thing is going at any given time? Right, if I plug in 2, that'll be its velocity in the 2-second mark. Now part B, find the distance travelled in 4 seconds. Well, this, again, you have to kind of go back to your calc world, or not so much your calc, but maybe your physics world or whatever. Hopefully some of you have seen this or know about it. But if you find the area under a velocity curve, isn't that the displacement? One node, 2 nodes. So 2 of you have been to a class. Can you remember where you were told that? Is it in physics or someplace?
Last quarter, I took the introduction to physics, and we talked about that.
Okay, so it's the intro to physics. Now, if you've not done physics, can you just trust me then that the area under that curve is what you're looking for? So the distance traveled is the integral from 0 to 4 of the velocity function. So it's the integral from 0 to 4 of 2t squared plus 2e to the t dt. Add 1 to the power.
Is
Nothing
it
much
3e
happens.
to the t squared?
Is it 3? Oh, thank you. Luckily, the answer's t cubed, so thanks for catching that. T equals 0 to t equals 4. Are we happy about the fact that once I write this thing correctly, its antiderivative is t cubed, and that the antiderivative of that is still 2e to the t? And now we're going to evaluate it at 0 and 4. If you plug in 4, you get 4 cubed. If you plug in 4 here, you get 2e to the 4. Take away a nothing plus, well, isn't that basically going to be 2e to the nothing, which is just 2? And since I'm running short of room, 4, 16, 64, 64 take away 2 is 62, plus 2e to the 4. And we are finished. We have got our distance. And that shows you the power of this process. If you can model, that's just a fancy name for it, if you can find a formula for the acceleration of a moving object at any given time, can't you then use this technique to find out what the velocity of that moving object is at any given time? And if you integrate further, you can even find the displacement. And we didn't do displacement, we just found the total distance. But you could find the displacement at any given point in time as well. And so I think that's pretty cool that you can do that. So that's the example similar to question 4 in your homework. Now, any questions about that? I should bring that back up. Any questions about that before I move on? Okay, that's a good sign. I'm going to show you some homework questions right now. Oh, I got somebody in the chat. What did they say? Yeah. Okay. Oh, actually, while I'm here, let's take attendance. Everybody say hi. Give me a few seconds to set this up as well. That's not what I wanted. Okay, that looks like we're ready. I've got this question in front of me. Hopefully you can see it. It says question 11. Great. Okay. The first part is find the general indefinite integral. Use C for a constant. Well, that's what we've been doing all day today, right? Finding indefinite integrals. So here goes. What do you get when you integrate a cosine?
Negative sign.
Sure about the sign? The plus or minus of the answer?
Negative sign. Sign X.
Well, yeah, which is it?
Positive.
Positive. I know it's a pain, isn't it? You're differentiating. Sine and cosine have always been the big bugaboo with students, right? Antiderivative of cosine is positive sine. Now, do you notice over here they've actually got the sine button? Now, I don't know, and I like playing safe. if you type from your keyboard S, then I, then N, and then put a bracket, an X and a bracket, it may actually recognize that as a sign. However, the fact that it's got a button that says sign on it might mean that you have to hit the sign button so that it knows it's a sign, right? So I'm just putting that out there as a warning. Right, now, this one's a bit weird. It's a fraction, 1/6 of x. So the power rule would be add 1 to the power, so that's x squared. Dividing by 2 is really a half, so what we end up here with is plus a 12. So we're going to go plus, and we're going to go back up here and do the fraction button, 1/12. And then we're going to move the little thing over, and then we're going to hit X, and then we're going to hit the square button. And I believe you can say plus C, but let me just double check that there isn't a plus C in the list. Okay, I am happy. You should just be able to say plus C, right? Now, that wasn't particularly difficult, except be careful with the antiderivative of cosine. Here are 4 members of that guy. Now, what they're talking about is, if you get your calculator, you type in sine x plus 1/12 x squared plus 0 plus 5 plus 10 and then plus -5. And when you put them together, one of these 4 pictures is what you've got. So what we're looking at here is the general indefinite integral, right? The one with the plus C, but we're still trying to essentially let the calculator help us. So, do you see a little calculator on my screen right now?
Yeah.
Okay, so let me show you what I would do here. First thing is a bit silly, but just make sure you're in radians. And now I'll get out of that. I'm going to go here and I'm going to go y equals. I'm going to do sine x. I'm going to add 1 divided by 12 in brackets x. That's how I do 1/12 x. If I did 1 divided by 12x, it wouldn't be the same thing. This calculator would think it was a 1 on the top, a big line, and 12x in the bottom. So you see why you have to need the brackets to force it to realize it's a 12th. I just put brackets around fractions anyway, as a safety measure. Right, so...
It is x squared.
Darn it. And... too busy talking. I wonder if that will do it. No. Shouldn't. I can't multitask. There we go. Work, I tell you. What? I don't know how. That was that. Right, now, if you put in the numbers -5, that's the first one, right? Subtract 5. And you do, I don't know, what kind of window should I do? I don't really care. Let's do -2 pi to pi. There's -2 pi. And there's 2 pi. Seems like a pretty decent window. Right, that's me set it up. What I've done right now, or what I'll be doing in a few seconds, is I'm sketching this guy here when the guy's -5. So when I do zoom 0, you'll see a whole load of, hopefully, wiggly curves. Okay, now I'm going to go back here, and I don't have time to do every single one of these, so I'm just going to do the +5 one now. So it's going to be the sine of x plus 1/12 of x squared plus 5. Now if I do zoom to fit, a few seconds to figure it out, you get one of them, And then you get the other one. Now, can you imagine I spent a little bit more time and filled in the other two in the missing, that are missing? Wouldn't my calculator be one of these four guys? Right now I can tell you it's definitely not this one. Would you agree it's pointing the wrong way? Just looking at the bottom one, out of the three that's left, does any of these guys, let's rephrase it. Can I kill this one for the same reason it doesn't look like that guy?
Yeah.
It's cosine.
Okay, so what's this fella?
The bottom left.
So we're going with this one here?
Yeah.
Well, it's the most
Yeah,
like
the shapes, yeah, I agree with you.
Couldn't
So
you just look at the whole function and just determine what would shift it? The only thing there that would determine that would be the sine wave.
Well, the shifting is found by the plus C, because if you do it +4, it moves it up 4. If you do +10, it moves it up.
Yeah, I just
Yeah.
meant with its behavior. I misspoke.
Yeah.
Sorry.
No, I know what you meant. So yeah, so that's kind of that weird question, if you're wondering what it is. So here's the last group of questions, and I'm only going to be able to tell you what to do without actually having time to show you me doing it. If you are given a rate function, that means something that tells you how things are changing through time, like the rate at which water is leaving a tank, the rate at which I make a profit, anything that has rate in it, bacteria growth rate, whatever it might be, and you want to find the total amount that's happened over a certain period of time, then you are going to find actually definite integrals. So I'll show you what this one is. Here is your function. Water is coming out at the rate of 400 take away 8t. It's going to take from 0 to 50. How much is going to come out in the first 30 minutes? That will be the integral of this guy from 0 to 30. Right, you just integrate the function, the rate function, from 0 to 30, because it's the first 30 minutes. Suppose it said the first 50 minutes, 0 to 50. First 10 minutes, 0 to 10. So for those who are not audio learners, I will be putting this on the screen in a few seconds, and you will see what I'm getting at. Right, let's show you what that guy looks like. So in this question, what you're being told is that water is coming out of a tank at the rate of 400 take away 8t. And you're being asked how much water is spewed out of the tank in the first 30 seconds, I think it is, 0 to 30 of the rate function. Now, if I tell you that c dashed of x, and I'm just making this up, 0.1, 2.3x plus 0.01x squared. And I want to know the production rate, or whatever they call it, but it's from 2000 to 4000. You just take whatever this thing is called and integrate it from, in this particular question, from 2000 to 4000. So you're going to go the integral from 2000 to 4000 of some really ugly, looks to me like a really ugly quadratic, right? Now you know how to do that. Isn't that just power rule with ugly numbers? That's all it is. And the last one, you're going to be finding the integral of 100, no, it's actually 1000, 5 to the power of t, dt. And in this story, you are going to find, oops, by integrating this, you are going to find the formula for the population. So this is going to be a generic indefinite integral with a plus c at the end. And then you're going to use the fact that the population at time 0 is 7,000. And that will get you this fella. Okay, since I've just got a few moments left, this is an indefinite integral, right? It doesn't have a start and finish number, but we can find its antiderivative. Isn't it 1,000, 5 to the power of t, divided by the natural log of 5? And then you plug 0 in here, set it equal to 7,000, and you'll find out what C is, and C is a ridiculously ugly looking thing, but it's still right. And I call that cutting it fine, because we have done everything that we need to get done today. We have finished with indefinite integrals. So Thursday and Friday is all about what's called the substitution method. So we're going to show you a different new method you haven't seen yet, and it allows us to find antiderivatives of much more complicated functions than we've dealt with so far. Okay, that was we learned some cool stuff today, didn't we?
Oh yeah.
Bye then. I'll see you all tomorrow.
Bye.